So here's the title of the talk: Quantum Annealing with AC Potentials. My main collaborator here is Elliot Caput, and well, Gianni Mossi on the second reference. This talk is based on these two references. And without further ado, the rough outline, the intended outline, is for me to give you some general pointers. As an outsider to quantum computing, I find talking about this helpful because that sort of organizes my own thinking. Then I'm gonna say a few very simple things about AC perturbations and tunneling, and then I will show results from two case studies. Okay. Okay. This is my rough sketch of how to think of adiabatic quantum computing, and the point of the slide is to contrast quantum computing and quantum annealing. And I probably wouldn't have this slide if I didn't have a particularly picky referee who sort of, you know, there were 3 pages of a lecture of just like, stop using these things interchangeably. And I think there's some logic there. So let me just try this on you. Right. The idea with quantum annealing is that you start on the, as a function of a tuning parameter, you start in the regime where you can prepare the ground state, say, as a product state. And then quasi-statically, you evolve this parameter to the place where you cannot prepare a ground state. And then the idea, initially at least, and I apologize, I don't have many references. You know, I tend to kind of focus on ideas, assuming that, you know, keywords nowadays you can Google, and you know, references are easy to come by. Right, but the idea is basically you prepare a ground state by some classical means, cheaply, and then physics gives you a state which is a mixture of some low energy, hard to prepare states. And the main difference, as far as I understand it, and the difference between quantum computing and quantum annealing is, with quantum computing, the solution of the problem is encoded in the ground state of a certain problem. And to reach that ground state, you might have to evolve for an exponentially long amount of time, but you want this state with probability 1 or appreciable. Whereas, which already sounds really impractical. Quantum annealing is a different idea, or similar but different idea, that there may be a bunch of states, and what you're trying to do is you're trying to get an approximation to a manifold that's hard to reach. And as you see that, you know, the notion of thermalization is kind of baked in there, that this problem is very hard to cool with Monte Carlo or other means. And in a way, what you want to do is you want an appreciable probability spread over all these states, and you don't necessarily care if these states are faithfully sampled, but they should be sampled maybe even with an infinite temperature distribution. Okay. Anyway, and so there's a general sense that being able to thermalize a classical problem is a powerful computational resource, and so here quantum annealing is basically giving you a tool to do that. So that's one set of notions. The other sort of practical issue is that if one builds a quantum computer to solve a computationally hard problem, usually all-to-all connectivity is kind of part of the wish list. And all-to-all connectivity is difficult to engineer, as you saw in Dima's talk. These are sort of local gates mostly. And the idea of engineering all-to-all connectivity is you have to go construct an embedding schema. And this is what's called minor embedding, where your qubits are strings of physical bits labeled by the same letter. And the idea is that all-to-all connectivity can be engineered if these logical bits contain n physical bits, and then in a 2-dimensional lattice, you can sort of make sure that A talks to all of the other letters. Okay. Now, this problem is n squared. And so if you're not careful, you know, if you need to have all physical bits tunneling, this problem can easily have bottlenecks or whatever, slow tunneling, which is not order n, but order n squared in the exponent. And this is a disaster. And these kinds of bottlenecks are the most things that we hear about, for example, analog optimization that's currently very actively being developed at Harvard and MIT, these Rydberg simulators and other places. This has, slowdowns of this sort of a adiabatic nature built into this. And so again, an outsider's perspective is that these methods are not worried about discovering shore-like breakthroughs. The idea is that these problems are hard enough that we don't have a hope to have a shortcut. But there's still quantum advantages baked in here. I won't say much more about that during the talk. I just want to focus on simple things. The last preliminary statement of orientation I wanted to make is that there is this time to solution heuristic that you see scattered in the quantum computing literature, at least some of it. It's kind of defined very empirically. You just sort of want a probability of success, which is, and this is basically developed to convert a small probability of success into the time to solution. You're basically trading statistical sampling of runs for the long integration time. I think this is the formula that people generally use. And so I think in trying to make sense of this formula, if we're in the regime where the probability of a transition that you seek is small but growing linearly in time, this heuristic that is often used, time to solution, is actually just inverse rate. And it's this inverse rate that's going to be exponentially small in the number of qubits. Okay, I just wanted to, identify the quantity that we're going to be targeting in all of this. All right. So in physics, we are used to slow processes, and they tend to be interesting because they're hard to estimate without a theory. By slow, the reason processes are interesting processes are slow is because they're collective. There's a bunch of degrees of freedom that have to tunnel. In elementary quantum mechanics, you're tunneling through vast expanses of space. So n is an action of some path that's long. And so there are many examples. And I think as a physicist, you kind of want to know what controls the constant. Let's assume that the scaling is as I wrote here, but that we want to know what the constant depends on. And the purpose of this talk is to consider certain kinds of AC perturbations to see how that affects this constant, and to just make sure we're kind of on the same page. I thought I would use something very familiar to illustrate the effect. So here's the Landau Zener problem. And you should think of this, I just want to anticipate, you should think of this as being a very small matrix element M, which is inherited from some Manybody problem. And so this is going to be exponentially small in something. Okay. And the thing that I want to emphasize is that unlike the conventional Landau Zener problem where we focus on adiabatic passage, I want to make sure that you're comfortable with the boring diabatic result, which is basically if you average this dynamics in some way, either over starting time or over the location of this crossing, you will find that the transition rate is m squared. And that's what you get from the Fermi golden rule. And in fact, there's a way to derive this using a variant of the Fermi golden rule. Okay, so can we do better? And the crux of the matter is to consider the same problem, but now consider very gentle, because we want to do things perturbatively as we can throughout all of this. So we would like to consider a small. We'll introduce a small parameter, which is the angle, the maximum angle by which the X perturbation oscillates in the XY plane. Okay. And what you find, and this is where the dynamical pathways that Peter was, talking about, I think that there's a way to think of it this way, but I just drew pictures. The idea is that if you think of the perturbation theory, opening up this perturbation theory, what you see is that there is a pathway by which you diabatically sort of make a transition into the state one across this avoided crossing. But there's another pathway where in the rotating frame, you have the same transition, but it's now shifted to a different value of G. But because there's a small alpha here, this thing is not just m squared, it's alpha squared m squared. Okay. And the idea here is that these diabatic pathways, because they happen at different times, they will not interfere. So you're allowed to add rates. Okay. Because this is a two-level system, you can just stick it in Mathematica and look at it. So this is time. This is black line is the usual, is the DC case, and the red trace is the AC case, and you literally see in real time the blips when the system makes the transition. And what you notice is that if you keep integrating this in time, and I'm not trying to build mystery here, this is a known result to people who study Landau Zener problems with AC perturbations. There's actually a back and forward symmetry. So if you keep integrating, there's another contribution that robs you of the gain. So you actually need to know where the crossing is enough to break that back and forward symmetry. Okay, so we don't want to integrate too long because we're going to lose our result. Okay, so that's basically the insight that we're going to scale up in the Manybody context. So we're not going to go to truly interesting problems. We're going to stay away from problems where there's lots and lots of ground states, spin glass complexity, and all these things. And the point that I want to just focus for the remaining of the talk is that there's actually a very clearly defined problem that has to do with fragility of adiabatic protocols. So now we're going to talk about the famous adiabatic protocols and how useless they are. Okay. Whoops. And this was appreciated very shortly after the proposal for adiabatic quantum computing. This is a PRL by Roland and Cerf. What they pointed out is that simply having a theorem doesn't guarantee that you win. What they pointed out is that, so this is the spectrum of the Grover problem. C is just some string that you don't know. And the idea is that there is a level crossing. And in order to achieve the famous sort of a square root gain in the runtime of this algorithm, you actually need to know exactly where the level crossing is to exponential precision. And if you don't know this, you're back to m squared scaling, which is the classical scaling, which is sort of the nice thing about the Grover search is because it's such a structuralist problem, it's very easy to not have any, to prove things essentially, not have any doubts. And so basically in this case, if you don't know where this crossing is, you cannot win. And so this is true of adiabatic Grover, and actually it was kind of obvious that it should also be true for the gate Grover when we were talking about this, but recently Miles Studenmeyer and his collaborators, they played around with gate Grover and they also saw similar fragility. Right, so the idea is that this is the problem that we want to solve. If I want to be able to retain some of the quantum advantage, but without the fragility to know, because this piece of knowledge is not going to scale up in a realistic setting. So at this point, I'm just going to draw some pictures, but then jump to like sort of the result. The idea is basically, let's take the same Landau Zener model, and let's imagine that this HG now refers to the Manybody problem. So it has a level crossing, say the same Grover, but now every single qubit is going to get its own frequency of oscillation. Then I'm just going to take the same picture, and I'll say that there's going to be n places where you can pre-kick the state into the excited state. And I'm just going to write the same thing down, except with a prefactor n. Now, initially, we thought, well, D-Wave has thousands of qubits. This is a huge boost. Let's write a paper. But then we started doing perturbation theory. And then you realize that there's something really interesting that happens. Well, the boring thing that happens is the thing that I circled. This is what you expect. You expect that there's now going to be tone combinations drawn here in purple. Like, so this is the second order perturbation theory, where the number of tone combinations that manage to resonate is n squared. Now, because we are doing perturbation theory, it's a smaller contribution. It's alpha to the fourth. But the thing that's really important is that these are all prefactors in n, right? They're polynomials. The thing that's exponential and that's killing you is this m squared. We would like to shift the exponent. And naively, you would expect that it goes from m squared to m to the fourth, and the answer is no. The answer is that each of these terms in perturbation theory has the same exponential scaling. And that's actually a really important and generic result. I'm not going to explain it in detail. I just want to give you a flavor, and you're welcome to think about it or talk to me. And the idea is basically that this is my attempt to sketch the excited states, which I don't care about. So usually if you have an avoided level crossing, there's the minimal gap. And the right way to think about this minimal gap is not that it's an energy scale, but it's rather a matrix element. You're trying to do some degenerate perturbation. Imagine going to a system where this is an exact crossing, and then you introduce a term in the Hamiltonian which mixes these states, and in degenerate perturbation theory, you will get a gap which is first order in the matrix element. Well, which matrix element, you might ask? And because these are many-body problems and these states are essentially unrelated, they differ by a large number of excitations. Almost any perturbation, it turns out, if you consider basically a matrix element somewhere away from this crossing of x1, y, xx, any kind of a local perturbation, it turns out that all matrix elements between these two states scale in the same way as the minimal gap. So this is such a natural thing that we looked for this in the early literature in quantum mechanics. Like it goes back to level repulsion essentially, but we couldn't find it. So we framed it as an M-scale conjecture that basically all matrix element and the minimal gap have the same exponential scaling. Okay. If you know any references, please let us know. The other thing I wanted to, but then there's another fact that's very important to keep in mind. Again, I'm just summarizing the ingredients. I don't want to spend time on it. If you expand the unitary in time-dependent perturbation theory and you project it onto just the doublet, what you find is that all of these terms involve lots of local excitations. And then there's one matrix element when you switch the valley, which state you're in. And this is so these two together these two facts is the reason. Actually, I have the slide repeated, so let me just keep going. So these two facts is the reason why as you keep doing time-dependent perturbation theory, these terms have the same exponential suppression. Okay. No time for that. The punchline is, and you can feel free not to believe it because I'm going to tell you something else next. The punchline is that if you look at the resummed perturbation theory, you have the exponential elephant in the room, the exponentially small elephant. And you've got this tower of kind of naive contributions, all positive and non-interfering, and they resum into an exponential which is softer. This is the punchline. There is an entropic contribution. In other words, in this dynamical situation, the system manages to find optimal photon combinations that give you transitions much more rapidly than the thing. Now, because we're talking about exponentials, the numerics are actually very easy to set up. And you can run them. So for an exponential, because this is all just proof of principle, we can run them for an exponentially long amount of time. And this is the time is chosen in such a way that optimal growth would be a flat line. The blue trace is the dynamical transfer without AC drive, and the green trace is the best sort of a AC driven case. So the punchline is that indeed this exponential, this collective tunneling exponent, the apparent collective tunneling exponent can be negotiated. And these simulations were run by statistically sampling frequencies, detunings. This was basically kind of a thing where, our intuition was that adiabatic passage is this very kind of a fragile, brittle thing that's a single trajectory. Whereas what we wanted to say is that, look, let's throw everything at this problem where we don't control anything, but we want to kind of know where the window is with polynomial accuracy, but sample over everything else. And that's what this is. Okay. Now I would like to, so one important question that everybody who studied these problems in the past asks is, what about heating? We know what heating does with flow K. I mean, we have an expert here in the front row. This is not a flow K problem. This has multiple frequencies. This should heat like crazy. And the important point is that we're talking about a ground state, the ground state manifold, and we have a gap of order 1. All of our frequencies are scaled down as 1/n. So we're trying to be maximally mixing within a very narrow range of energies and be completely adiabatic with respect to the rest of the spectrum. Okay, this is why we keep calling this cold thermalization when we talk among ourselves. So I have 5 minutes left. Okay, good. So this is sort of the basic mechanism. Whoops. This is sort of this idea of accelerating collective tunneling without heating the system up is sort of the basic mechanism that was in the first paper. And when we tried to apply these ideas to actual qubit sort of a setups, we had harsh kind of reality checks. In particular, these are the kinds of problems that we're interested in. But then in the actual experiment that there was a chance of us running this on, it was a purely ferromagnetic problem. So we're like, well, all of these proposals for spin glasses and whatever, what do we do with a ferromagnet? And that's how we realized that, wait a minute, ferromagnets are the building blocks of that minor embedding. So maybe there is something interesting and worth talking about. So this is the problem that we tackled in this preprint. And it's pretty easy to define, and there's only 2 slides. It's like one of these things, once you build up this kind of like set of intuitions and yeah, internal lingo, you can basically just switch gears into a completely different problem. And this is what's referred to as reverse annealing. This is time. We consider the everybody's favorite transverse field Ising model, and we're going to think of couplings which are mostly familiar. In other words, the transverse field, which we denote by kappa, is going to go from 0 to somewhere below 1 and go down. But the whole time that we're doing this, we're also going to add very weak and very slow perturbations, AC perturbations. This is not noise. Basically, that's another question that people ask. If you have lots of frequencies, why is it not noise? Well, we have at most n frequencies. For these simulations, because of experimental constraints, we had far fewer frequencies, square root of n. And the basic question we're going to ask is the same. There's an exponentially small elephant, which is the probability of the full magnetization reversal. And this is the famous instanton in the standard case. It's basically tunneling of all up to all down. So if you just run this and come back with none of these AC perturbations, you'll see an exponential, which tells you something about the domain wall, sorry, the instanton gap. So that's one observable that I'm going to plot. And the second observable is the equal time autoparameter, which is the square root of this thing, whilst the AC fields are on. And this is basically just our insurance policy to make sure that when we see something interesting in the tunneling, it's not because we accidentally left the broken symmetry phase. We want this thing to be ordered. This is the punchline. The probability of magnetization reversal, and again, remember what we do is that we'll look at it for it be growing linearly in time. We take the rate, and the rate is exponentially decaying in n, in L system size. The insets here are transverse field 0.7. The main plot is transverse field 0.9. The black traces are all in the absence of AC fields. That's our kind of like baseline. And the color traces are different AC protocols. And what you see, what you should observe is that, let's start here. So kappa equals 0.7, that's safely away from the critical point. We see that, okay, it's exponentially going down, and the exponent is negotiated to be softer, so it's faster tunneling, good. That's what we expect. This is the safe regime. But then we find really interesting behavior where this, for some of these protocols, the exponent stops growing as a function of L. It's small, but it's flat. So the rate is kind of just whatever, maybe powerful. Meanwhile, the autoparameter is still finite and pretty healthy, right? You can see, just go back and forth. And so this is sort of an example where we seem to have accelerated the ground state dynamics without paying the cost of, for larger systems. By the way, these simulations have very low entanglement, so these were done with TBD, right? You can actually do time-dependent integration of all of this and kind of get away with it. And that's the punchline. That's basically the punchline. So I don't know what these results really mean, unfortunately, because we've, as I said, that previously when we had maximal randomness, we actually could average over things and kind of like think of it theoretically, because here the number of frequencies in the protocol is sufficiently correlated We kind of like did the machine learning except the human way. You just keep trying it until the results look nicer and nicer and nicer. So we don't actually know how to do theory on this yet. I have some ideas, but this is basically the punchline, that we have a state here which does not heat. We don't excite any domain walls. The ground states are mixing like crazy. And the order parameter is still, because we don't heat, we essentially, the order parameter stays pretty finite. And I think this is it. So the punchline here is that if you have a favorite system where there's slow tunneling and you want to make it faster or maybe even slower, I was thinking about this during Dima's talk. There's a whole bunch of knobs having to do with perturbations that don't heat the system up, but nevertheless they agitated, that might be worth considering. There are lots of experiments that would be worth doing to kind of test this, in part because all of the theory we've done is isolated many-body systems, and multi-photon processes you might think will be very fragile to open system sort of issues. Okay, I think I should stop. I see Elio getting up, so I think I said all I need to say. I mean, thanks.